Next circuit is BCD adder. So before going to design a circuit or implement the circuit, let us look at the rules of BCD addition. So we know the important rule for BCD addition is, the first assumption is that we are going to add two BCD numbers. That means the range is from 0 to 9 and those are represented in their 4-digit binary value. And we are going to add those two numbers and the resultant will be also a BCD value. Okay. So that means if I am having 10 as a number, I will be getting 0001 and 0000. Likewise, I will be getting the result. So talking about the rules, now when we add two BCD numbers and at that time the resultant should be checked with the valid BCD or invalid BCD. If we get the resultant as invalid BCD or a carry generated, then we are going to add 0110. Why? Because the BCD numbers are ranging from 0 to 9. We are using 4 bits. So 6 combinations are unused. That's why we are using this 0110. So this is the important question, can be asked in your oral examination. That's why I am repeating it. We have discussed it earlier in our lecture timing. But this is what the reason. So whenever an invalid BCD is generated or carry is generated as a result, we need to add 0110. And if valid BCD is there as a result, we are going to carry forward the result. That means we are going to add 0. That means either we will be adding 0110 or we will be adding 0000 in the result. So based on that, we have designed a circuit. So in that we have to add, we have to use two binary adders. One for performing normal BCD addition, that is first binary adder will perform the addition of two BCD numbers, and the second binary adder is used for either adding 0110 or 000 based on the validity. If invalid BCD is there or carry is generated, the second binary adder will add 0110. If a valid BCD is there, second binary adder will add 0000. Okay, so I have taken these three examples over here. 2 plus 8. The 2 and 8 represented in BCD. This is what the number is. It is invalid BCD. So I have added 0110 and this is what the resultant is. So this is what a carry of the second binary adder. Okay. And this is a BCD. Okay. So whatever carry is generated, that we have taken, and this is the BCD. Now next part is the second condition, when the carry generated, we need to add this 6 and this is what the resultant is. And for valid BCD resultant, the 000 is added and this is what the final result. We will be taking these three as the test cases for my circuit. That's why I have solved it here. Okay. So this is what the circuit we have designed during our lecture time. So these two 4-bit binary adders are required and the ICs are 7483. I have provided you a reference chart. I hope based on that you have put the pin numbers like this, right? So this is what a 4-bit binary adder chart is, 7483. So referring to this, if this is the 7483 chart and I have to put the pin numbers. So A0 is the first input which is having the 10th pin. A1 is the second input bit for the first BCD number, that is 8. A2 is 3. A3 is 1. Likewise, as I am adding two BCD number, this will be considered as the combination will be considered as the first BCD number. This 4 bits combination is considered as the second BCD number. So B0 is here. B0 is 11. So I'll put 11 here. B1 is 7. B2 is 4. B3 is 16. Okay. Then we have C in also in our circuit. So C in is 13. We need to use C out, that is 14. Then S0 is my first output bit, 9. S1 is second output bit, that is 6. S2 third output bit, that is 2. S3 is 15. So likewise, we have to put the pin numbers for both the binary adders. I will be using two binary adders. First, for performing simple, whatever inputs are provided, those inputs are to be added by simple binary adder. Whatever resultant is there, we have to check on that result value, whether it is an invalid BCD or valid BCD, and based on that we'll be adding either 6 or 0. So this is what the logic behind that. You just get the revision of this. We have already discussed in our theory part. So here 2 binary address are required, and for checking of the validity, this is what the logical circuit. So again, for second binary adder, referring to the chart, I have marked these pin numbers. Now these are the AND and OR gates required: 1 2 3 4 5 6, 1 2 3 4 5 6, and this is the carry taken out. This is what the resultant carry is. So this way this carry is obtained. This carry is obtained from this value, and this is what the final output can be obtained by second binary adder. Okay, so the same thing is implemented here. I am not purposely showing pin by pin connection here because of the lack of time, because we need to cover both the circuits, XS3 adder and BCD adder. I have done the circuit implementation already. I will just show you how inputs and outputs are taken and checked. Most importantly, here VCC and ground connections for all the ICs is important. For 4-bit binary adder, 5th pin is VCC and 12th pin is ground. For the gate ICs, 7408 AND gate, 7432 OR gate, the 7th pin is ground and 14th pin is VCC. So based on that, the rest of the connections are done. Okay, now whatever example I have solved earlier, let us check it with the connections made. Okay, so I will show you XS3 connection, XS3 adder connections in detail one by one. But because of lack of time, and as this is somewhat complicated circuit, I have made the implementation already and just showing you how input output combinations are cross checked. So this is the connection made. Initially these 4 inputs, this is considered as A0, A1, A2, A3. This is B0, B1, B2, B3. This side, this is S0, S1, S2, S3, the final output, and this is what the carry we have to check. Okay, so these are the input combinations, these are the output combinations. Now the first example we have taken, if I have inputted 2 plus 8, that means my first A combination will be 2 and B combination will be 8. So what should I get at the end result? 1 as a carry and 0, 0, 0 as a S0 to S1, S2, S3 value. Okay, so let us cross check it. Now this is what my A0 to A3. So I need to put 2 over here. That is 2 plus 8. This is MSB. For this 4-bit, this is MSB. For this 4-bit, this is MSB. So 0, 0, 1, 0. 0, 0, 1, 0 plus 1, 0, 0, 0, 1, 0, 0, 0. So what output is expected? Carry bit should be 1 and my S0, S1, S2, S3 should be 0, 0, 0. Look at the output. The carry is 1 and all the outputs are 0, 0, 0, 0. Okay. So the first case is checked here. Now the second case. Now here in the resultant we got the invalid BCD. Now the second example is taken in which the carry is generated. For that I have taken an example of 8 plus 8. So my both the input values will be, now this is 8, the second is 8. So A is 8, B is 8. So what is the output expected? Carry should be 1 and S0, S1, S2, S3 status should be 0, 1, 1, 0. So check at the output. 0 carry is 1 and this is 0, 1, 1, 0. That is 1 and 6, that is 16. Okay. Now the third case where the resultant of first binary adder, the output is a valid BCD. So let us take small numbers. So it is 2 plus 2. Okay. So our expected output is 0, 1, 0, 0, that is 4. So the output is 0, 1, 0, 0. Let us take one more example. Suppose 4 plus 2. Again it is a 4 plus 2, that is 6. It is a valid BCD resultant. So output is 1, 1, 1, 0. Okay. Now let us take 9 plus 9, because 9 is the last BCD value. So 9 plus 9 should be 18. So 9 plus 9. So 18 is carry is 1 and this is 1, 0, 0, 0. Okay. I hope you understood how to check the inputs and output. In this practical, the important thing is for the orals is to remember the rules for addition. What is difference between binary and BCD? what are the rules for BCD addition, why to add 0 1 1 0 if invalid BCD or the carry is generated, and what is the logic behind designing the circuit. For that we have generated a truth table, and then based on that we have identified an equation, and then we have designed it. Okay, so the method for identifying this logical circuit that you should revise from a theory part, and then the designing of this circuit. So these parts are important here as per BCD adder. Okay, so let us look at so already we have seen accessory adder as well. So just go through the details of the implementation from theory part. Okay.